Hello everyone. This is part 4 video on past year NEET questions from the topic work, energy and power. Those who are looking at this video can take a look at the previous part so that you will have continuity of questions. We'll start with a question that has come in the year 2011. For a force F acting on a particle moving in a straight line which varies with the distance d as shown in the figure. Means they are giving us the relation between the force and distance of the particle in the graphical representation. The work done on the particle during its displacement of 12 meters. So here when they are using the distance and displacement in equal sense, it basically means the particle is going along a straight line without changing direction. So here the force and the displacement, they both are in the same direction. Now it's a variable force. For a variable force, right, if you consider a small displacement dx, then the work done in that small displacement will be f dx. We want to find the overall work done, means we have to integrate it. Now graphically the work will be represented by area below the force and position or displacement curve. So here the way it comes is, if you take a small displacement dx, right, we look at what is the corresponding force there and we multiply. F dx will be equal to the area of the small rectangle that you see over here. If you add all of it, means what is it going to give us? Essentially it will give us what is the area between the force curve and the x-axis. So here we need to find what is that area. If you observe it, right, from 0 to 3 the force curve is not there. Basically means, you know, it is coinciding with the x-axis. From 3 onwards it is starting, so suddenly it is reaching the value 2. From there it is maintaining constant value for some time, then it is decreasing. So area below the curve means this is what it is going to be. So we can see the area can be divided into two parts. One is a rectangle, other will be a triangle. So in fact the demarcation is given there itself. It makes our job a little bit easier. So we'll see that there are two parts to the area 1 and area 2. So part 1, what will be the area? It's a rectangle with a width, we can say 4 meters, and height is 2 newtons. So in this case the work will be what? 2 newtons into 4 meters, that will be equal to 8 joules. For the part 2, which is a triangle, base will be 7 to 12, means base is 5 meters and height again is 2 meters. So what is the area of the triangle? Half into 2 newtons into 5 meter. So 2 is cancelled. This is 5 joules. Total work done means we have to add up the area 1 and area 2, which will be equal to what? 8 joules plus 5 joules, that will be 13 joules. That is the total amount of the work done. So in fact we have seen in one of the other videos also a similar question, the measurement of work by using the force and displacement graph. Next we have a question that has come in the mains paper 2011. A mass m moving horizontally along the x-axis with a velocity v collides and sticks to a mass 3m moving vertically upwards along the y-axis with a velocity 2v. Means this m is moving along the x-axis with a velocity v, means we can say it is what? V into I cap. And the 3m is moving along the y-axis with a velocity 2v, means we can say that the velocity will be what? 2v into the j cap. After collision they are both sticking together and moving, means what? They will stick together. So this total mass will now be what? M plus 3m, that is going to be 4m. This is going to move. Now we need to find what is the final velocity of the combination. So here the final velocity of the combination, right, will be found by using the conservation of momentum principle, because for any collision they need not have to mention what is the type of collision. For any collision the total momentum of the particles will be what? Conserved, because collision is an internal phenomena, which means look at what is the initial momentum. A momentum of this mass m will be what? M into v I cap. And what about the momentum of the 3m? 3m into 2v the j cap. Okay, now the final velocity of the combination, let us say it is some v dash. So the final momentum will be what? 4m is the mass now, because it's moving together, 4m into v dash. So we can see on both sides m will get cancelled. So what is it? V into I cap, left hand side, plus 3 into 2 is what? 6v into the j cap. This is equal to 4v dash. We are looking for v dash, right? So we have to bring the 4 to the left side. 4 will go to the denominator, right? So v I cap by 4 plus 6v j cap by 4. That is our v dash. So if we just simplify one more step, what do we have? It will be 1 by 4 v into I cap, plus here we can cancel 2 3s are 2 2s are. That is what? 3 by 2 v into the j cap. That is our v dash value. So we are able to get the value by using the conservation of momentum principle. So what is the correct answer for this? It is option B, 1 by 4 v into I cap plus 3 by 2 v into the j cap. This is our final velocity of the combination. Next we have another question based on collision. This has come in the year 2010. A ball moving with a velocity 2 meter per second collides head on with another stationary ball of double the mass. Means they are not giving us the masses, right? So let us say the first object is what? Mass m. It is moving with a velocity 2 meter per second. Head on collision means the velocities of the particles before the collision as well as after the collision, they will be confined to a straight line. Now it's at rest. The double the mass object is basically at rest, stationary. If the coefficient of restitution is 0.5, then their velocities after the collision will be. So if you just take the initial velocity before the collision as u1 and u2, and final velocities after the collision as v1 and v2, then first thing that we'll have is for any type of collision, right, conservation of momentum principle will be applicable, because collision is an internal phenomena, correct? Which means what? The momentum of this ball m will be m into 2 initially. Momentum of the 2m will be what? 2m into 0. Why? Because it's at rest, means u2 value is 0. u1 value is what? 2 meter per second. This should be equal to the final momentum is what? For the first ball, m into v1, plus for the second ball it is what? 2m into v2. So this is anyway 0. So what do we have on both sides? We can cancel m. So 2 is equal to v1 plus 2v2. This is an equation in terms of v1 and v2. Okay, let us call it as equation 1. Now we have to get, because there are two variables, right, we should get one more equation, then only we can solve for the values of v1 and v2. Essentially what they are asking in this question, they are asking us to find the values of v1 and v2, right? Now the other information they have given is the coefficient of restitution. What is coefficient of restitution? Generally we'll define this coefficient of restitution for the head-on type of collisions. It is what? The relative velocity of separation after the collision divided by the relative velocity of approach before the collision. That ratio is what we call as the coefficient of restitution. So if you look at it, right, the u1 is approaching or rather the mass m is approaching 2m. So the relative velocity of approach, right, if you see with respect to 2m, means it will be like m is approaching. That will be equal to what? u1 minus u2. That is the relative velocity of approach. And relative velocity of separation after the collision means, if you look at with respect to m after the collision with respect to m, right, it will appear as if the 2m is receding or moving away. So the relative velocity of separation after the collision will be v2 minus v1. So we'll observe with respect to m. So the ratio of them is the ratio of relative velocity of separation, which is v2 minus v1 by u1 minus u2. This is a very important formula, people remember it. This is what is the coefficient of restitution. Okay, now this is given as 0.5, right? We know u1 and u2, so we'll just have to substitute that. So what is it? Coefficient of restitution is given as 0.5. So 0.5 is equal to what? V2 minus V1 divided by U1 is 2, U2 is anyway 0. So we'll take the 2 to the other side, it will go to the numerator. 0.5 into 2 will be what? 1. 1 is equal to V2 minus V1. 1 will be equal to V2 minus V1. So from here, if you rearrange, right, we can say minus V1, let us bring it to the left side. It will become what? Plus V1. So V1 will be equal to what? V2 minus 1. V1 will be equal to V2 minus 1. Let us keep it as equation 2. Now what we'll do is straight away we'll take this value of V1 and substitute. Substitute in the equation 1, what do we have? 2 is equal to, in place of V1 we'll put V2 minus 1 plus 2V2. Okay, which means what? Minus 1, let us bring it to the left side, it will become plus 1. So 2 plus 1 is 3. 3 is equal to V2 plus 2V2 means 3V2. So from here V2 will be equal to what? 1. V2 will be equal to 1. If V2 is equal to 1, then we can find V1. What is it? 1 minus 1, that is 0. So V1 is 0, V2 equal to 1. So check which of these options is corresponding. V1 is equal to 0 and V2 is equal to 1. So we have to take in the same order because they are mentioning mass m as the first object and mass 2m as second object, right? So we should give first the velocity of m, which is V1. V1 is what? 0, and V2 will be 1. Not here, but sometimes what they can do is they can also give one more options by interchanging the values. Means they could be giving another option saying 1 comma 0. So we should not get confused. We should follow the same order in which they are giving the. Next we have a question that is based on the water pump. An engine pumps water continuously through a hose. So basically what we call as the hose pipe, right? So this is how we'll have, this is the common hose pipe that is used generally to move the water from one place to other place with the help of the pump or the engine. Water leaves the hose with a velocity v, and small m is the mass per unit length of the water jet. So here small m is what? Mass per unit length. What is the rate at which kinetic energy is imparted to the water? So we need to find what is the rate at which kinetic energy is imparted to the water. So if you look at it, right, so we'll usually take this water from a vessel or a container where the water will be initially at rest. So we put this pipe and that will basically be connected to the engine. So the engine will be pumping the water to the pipe. So this is how the water will come out of the pipe. It is coming out with a velocity v. Now we need to find what is the kinetic energy imparted to the water. So how the water is able to gain the kinetic energy? Because of the engine. So if say for example in a time t, let capital M be the mass of water that is delivered. So in a time t, we are saying what? Capital M is the mass of the water that is delivered. Okay. So this mass of water is initially coming from the vessel, which is at rest initially, and finally it's having a velocity v, right? So what is the gain in kinetic energy for this mass m water? Half m v square, because initially that does not have any kinetic energy. Finally, what is the kinetic energy? Half m v square. So gain in kinetic energy will be this much. Now how is this gain in kinetic energy coming? Because of the work done by the engine only, right? So the work done by the engine is nothing but equal to the gain in kinetic energy of the water. So generally this relation, right, we will be using when somebody will ask us a question on the power of the engine. But here the question is about what? It is about the rate at which the kinetic energy is imparted to the water. So the kinetic energy given to the water in this case is what? Half capital M into V square, right? That is the kinetic energy gain. That is the kinetic energy imparted to the water. In how much time? In a time small t. So the rate at which kinetic energy is imparted. Rate means what? Always we have to divide this by the time taken, right? Which is what? Half capital M into V square divided by t. So if you look at it, right, so we can write it like this: half capital M by t into the V square. What is this capital M by t? Capital M is, we are saying, mass that is coming out, right? Divide by t means this is what? Mass flow rate, means the rate at which the mass is coming out of the hose pipe. That is not given. The information that is given to us is what? What is the velocity with which the water is coming out and mass per unit length of the water jet. So look at this. If we take a time t, the water is coming at a velocity v, right? So what will be the distance moved by the water jet in a time t? The distance moved by the water jet will be what? V into t, right? If you multiply this V into T with mass per unit length, small m is what? Mass per unit length. This is what? The total length that is moved by the jet. If you multiply this with mass per unit length, what we are going to get? What is the total mass of water that is ejected? Correct. So understand carefully. What is it? It's coming with a velocity v. In a time t, it will travel how much distance v into t. Means this entire amount of length water has come out, right? How do you know what is the mass of this? Multiply this with mass per unit length. We will get what is the mass of water that is ejected. So small m into V into T. This is the mass of the water that is ejected in how much time? In a time t, right? So if you divide that by t means what you will get? You will simply get what is the mass flow rate. What is the rate at which the mass is coming out? And what is it numerically equal to? Small m into V. The mass flow rate is numerically equal to what? Small m into V. Okay. Now which means in place of this capital M by T, what we are going to substitute here? Small m into V. That's it. We got the answer. So what is the rate at which the kinetic energy is imparted to the water jet? It is what? Half into capital M by T means mass flow rate, right? That is nothing but small m into V. So half into small m into V into another V square. What is it? Half into small m into the V cube. It's a very standard formula. So if you are pumping water using a hose pipe, right? Generally, you know, the water pumps will be used either to move the water up or, you know, to move the water on the horizontal ground. So the hose pipe is generally used to move the water on the horizontal ground. Okay. So here we will only talk about the kinetic energy of the water changing. The other use of the water pump will be to move. So from the ground we might want to move the water up into the overhead tank or something like that. That is another use of the water pump. So what is the answer for this? The rate at which the kinetic energy is imparted to water will be what? Half into small m into V cube. It's a standard formula. What is small m? Represents mass per unit length of the water jet, and V is the velocity with which the water will come out of the hose pipe. Okay. Now we have one more question, as it is based on the same formula. An engine pumps water through a hose pipe. Again, water passes through the pipe and leaves it with a velocity 2 meters per second. Same concept, right? So the water is coming out from the hose pipe with how much velocity? This is V. V is what? 2 meters per second. The mass per unit length of the water in the pipe is 100 kg per meter. Means small m value, right? Just now only we discussed about it. Is what? 100 kg per meter. What is the power of the engine? So as the water is leaving this hose pipe, right? In the previous question only we talked about it. The kinetic energy imparted to the water rate at which kinetic energy is imparted to the water. So we have got the formula for that, right? What is it? Half into small m into the V cube. Now this is also assuming this water engine or water pump is under 100% efficiency. Whatever the rate at which the kinetic energy is imparted to the water, the same will be the power of the pump, because where the kinetic energy for the water is coming because of the work done by the pump, right? So whatever the rate at which the kinetic energy is imparted to the water, same will be the power of the pump, which means what will be the power of the pump formula? Half into m into the V cube. So what is it? Half into small m is what? 100. Everything is in the SI system, so power is going to come in the SI unit, watt, into V cube means what? 2 cube. So half into 100 into 8, that will be what? 2 ones are 2 fours are, that is what? 400 watt, which is our option A. Now in some cases what might happen is the water pump might not be operating at 100% efficiency. In that case, what we'll do? We'll define something called as efficiency factor. We'll define something called as what? Efficiency factor. So efficiency factor will be the rate at which kinetic energy is imparted to the water divided by the electrical power of the engine or the pump. So in this case, what are we assuming? We are assuming that this value is equal to 1. Efficiency factor 1 means what? 100% efficiency. But practically speaking, what happens? If we are deriving some amount of electrical power, then not all that will be getting converted into the gain in kinetic energy for the water, right? Only a part of it will be converted. Hence, we will have the efficiency factor, practically speaking. Okay. So this is how we will solve questions on the hose pipe. A particle of mass capital M starting from rest undergoes uniform acceleration, means it is starting from rest. So the initial velocity will be what? 0. It undergoes uniform acceleration if the speed acquired in time t is capital V, means if you look at a journey of capital T time, the final velocity is what? Having a magnitude V. The power delivered to the particle is how much? It's a rather straightforward question. We can first look at the particle, right? When its speed or velocity is changing, it will have a change in the kinetic energy. Here there is no mention about the potential energy aspect. So based on the work energy theorem, right, work done by any force on that object will be equal to what? Change in kinetic energy. Here there is no mention of potential energy. Otherwise we would have said work done on that object is equal to change in kinetic energy plus change in potential energy, right? So change in kinetic energy means what? Final kinetic energy is half mv square. Initial kinetic energy, this is rest 0. So the work done is equal to what? Half into capital M into V square. This work is done in how much time? A time capital T. So what is the power delivered to the particle? Work done by the time taken, right? Which is what? Half mv square divided by time. So what is it? Half mv square by T. The correct answer for this is option D. A block mass m is attached to the lower end of a vertical spring. The spring is hung from a ceiling and has a force constant K. This force constant we'll also call it as what? Spring constant or stiffness constant, like that. This mass is now released from rest with the spring initially unstretched. Means what? Look at this. So we have a spring which is in the natural state or the unstretched. We are attaching a mass m. We are releasing it. Now when you release it, what is going to happen? The mass will have its weight, so it will start going down. The mass will start going down, and when the mass is going down, right, the spring will keep getting elongated. You will reach a stage somewhere where, see, when the spring is getting elongated, right, the spring will be gaining restoring force. You will reach a stage where the restoring force in the spring, if say for example x is the amount of elongation, right, so restoring force will try to pull the mass back to the original position, right? It will be upwards, acting on the block upwards. the restoring force will be able to balance the weight. So what is that x value we'll get? We are simply balancing the weight with the restoring force. Okay, so this x, right, is basically the elongation the spring will have till it reaches this point. What is this point? Where the restoring force of the spring is able to balance the weight. But the question they're asking is what? The maximum extension produced in the length of the spring. Do you think the block is going to stop here? No, because the block is still having some velocity downwards, because it is keep on moving down, right? Now, as the block moves further down, spring force value will be increasing. Weight will not change. So as a result, what is going to happen? The upward force will be more than the downward force. So now what we see is that the block will be under deceleration. It will go to this extreme position. You know what is this extreme position? The extreme position is nothing but the point where the velocity of the block will become zero. If you look at it, right, we'll talk about it in the oscillation chapter. This position, right, will be called as what? The equilibrium position. There the object will not actually stop. From there it will go to the extreme position. So this is the extreme position. So from our original level, it is coming down by, say for example, x dash. From the original level, it is coming down by what? X dash. Initially, the block is at rest, does not have any kinetic energy. Here also extreme position, it will be at the momentary rest, no kinetic energy. But the block is coming down, right? Coming down by how much? A distance x dash. So it has lost potential energy, mg into x dash, right? This is what? Loss in the potential energy for the block. Now what is happening to this potential energy? This is converting into, because there is no change in terms of kinetic energy. Initially when we are releasing it, it is at rest. At the extreme position also, that is at rest, no change in the kinetic energy. What is happening to this loss in potential energy? It is getting into the gain in the spring potential energy. So initially the spring is in the natural state, spring potential energy will be zero, but here the spring is elongated by a value x dash, right? What is the gain in the spring potential energy? Half k into x dash the square. Now whatever is the loss of gravitational potential energy for the block will be equal to what? Gain of spring potential energy, right? Because other than the gravity and the spring force, right, there are no other external forces, and gravity and spring force, both of them are taken as the potential energy term, which means what? There is no external force. So the total energy will be conserved, kinetic energy plus potential energy terms. Here we have two potential energy terms, spring potential energy and then gravitational potential energy. Whatever is the loss in the gravitational potential energy for the block when it is coming down will be converting into gain in the spring potential energy, so that there is no energy loss. Okay, which means what? We simply have to equate both of them. So mg into x dash is equal to what? Half k into x dash the square. So one of the x dash will be cancelled. So look at it, we will bring the 2 to the left side, it will go to the numerator. 2 mg by k, that is our x dash. So they're asking us what? The maximum extension produced in the length. What is it? 2 mg by k. So here you observe it. When we reach the equilibrium, right? You see what is the equilibrium extension? Look at this x value. What is this equilibrium extension? That is mg by k. So when we come down by a value of mg by k, we will come to the equilibrium. That is not the position where the block is going to stop. The block will keep moving further down because it will have velocity. It will finally go to the extreme position, and we'll see that the elongation is what? When it reaches the extreme position, what is it? 2 times mg by k. Next we have a question that has come in the 2009 paper. A body of mass 1 kg is thrown upwards with a velocity 20 meter per second. It momentarily comes to rest after attaining a height of 18 meters. Means what? This is the maximum height. How much energy is lost due to the air friction? So we are projecting or throwing a body up with how much velocity 20 meter per second from the surface. It is going up. How much? 18 meters. This is coming to rest. Now while it is moving, we need to find out what is the energy lost due to the air friction. So generally we'll assume that there is no air drag or air resistance, but in this question particularly we have to find what is the energy lost due to the air friction. So here, if you consider that there is an air friction, right, then as the body is moving from point 1 to point 2, here we'll apply the work energy theorem. What is it? Work done by this air friction will be equal to what? Change in kinetic energy plus change in potential energy. So as it is moving from point 1 to point 2, work done by any external force will be equal to what? Change in potential energy plus change in kinetic energy, right? So look at this. Here when we are projecting it, what is the K initial? Half into mass is 1 into 20 square. That is what? 20 square is 400 by 2 will be what? 200. It is joules. What about the Ke final? It is coming to moment rest, means 0. Surface will take as the reference for the potential energy, right? It's what reference by the potential energy, so it will be taken as 0. When it is at a height of 18 meters, means what is the potential energy value? M into G, will take it as 10. That's what they have given us. Into H. H is what? 18. So what is it? 18 tens are 180. So look at this. Work done by the frictional force will be equal to what? Change in kinetic energy. Final kinetic energy minus initial kinetic energy plus change in potential energy. What is the PE final? 180 joules minus initial is what? 0. So what is this? Minus 200 joules plus. So what do we get? Work done by the frictional force, the friction because of the air. Okay, what is it? Minus 20 joules. So what we'll say? The 20 joules of energy is basically lost due to the air friction, isn't it? So the work done by the air friction is what? Minus 20 joules, means we'll say 20 joules of energy is lost due to the air friction. So what is the correct answer for this? It is option D. Next we have a question on explosion. This one has come in the year 2009. An explosion blows a rock into 3 parts. 2 parts go off at right angles to each other. These 2 are 1 kg, which is moving with a velocity of 12 meter per second. 2 kg one, which is moving with a velocity of 8 meter per second. Okay, these 2 are going off at right angles. If the third part flies off with a velocity of 4 meter per second, they are even giving us what is the velocity of the third part. What would be the mass of it? Okay, so we need to find what is the mass of the third part. Okay, so look at this. Here if you look at the rock, initially we'll consider that this is at rest, means what? The initial momentum. What will be the initial momentum of the rock? It will be what? 0. Now when it is exploding into 3 parts, right? Remember, the explosion, just like collision, is an internal phenomena. Means during explosion, right, there will be no external forces. As a result of it, the total momentum of the system of particles will be conserved. Which means what? Look at, the way we will represent. It is dividing into 3 parts, right? 1 kg is moving at 12 meter per second. Okay, so this is how the 1 kg is moving with how much speed? 12 meter per second. 2 kg is moving at right angles at what speed? 8 meter per second. Now if you look at it, right, the third one will have to move in such a way that the total momentum of these 3 particles will add up to 0. Why they have to add up to 0? Because the initial momentum of the rock is what? 0, right? So finally, when we add up all the momentum, because momentum is a vector, when we add up momentum of particles, that should be adding up to 0. So what we do is, before we go and discuss about the third part, let us look at just the momentum of these two parts. What is the momentum of this mass into velocity, which is 12? Unit will be kg meter per second, SI unit. What about this one? 2 into 8 is what? 16 kg meter per second. They are at right angles. Both the momentum are at right angles, right? Now the resultant momentum, if you call them as P1 and P2 for each of them, then the P1 plus P2, right? Resultant momentum will be somewhere like this. The resultant will be along the line between the two directions, right? So we'll have to find what is the resultant momentum magnitude. What will be the resultant momentum magnitude? The resultant momentum P1 plus P2. What is it? Right angles, right? The angle between P1 and P2 is what? This is P1, this is P2. What is the angle between them? 90. So the resultant is what? P1 square plus P2 square whole root, which is what? Root of 12 square plus 16 square. So how much is it going to be? Root, this is what? 12 square means 144, and 16 square means what? This is 256. What is 144 plus 256? That is 400. What is root 420? So the resultant momentum is what? 20 kg meter per second. Now the third part should fly in such a way that P3 magnitude should be 20 kg meter per second, but direction should be exactly opposite. So P3 should have a magnitude same, 20 kg meter per second, but direction should be opposite. So when you add all the three, that's why they will become 0. Which means what? The P3 magnitude wise should be equal to what? 20 kg meter per second. And what will be the magnitude of the momentum? Mass of that third, let us call it as m3, into the velocity. What is the velocity? 4 meter per second. They have given us the velocity, right? So check it. 4 ones are, 4 fives are, right? Meter per second is cancelled. So what is the m3 value? 5 kg. So the third part, which is flying off, right, should have a mass of how much? 5 kg. So this is about this part video, and we'll see in the next part.